Welcome to Astronomy at McKendree University. This is your Thanksgiving week lecture. Instead of meeting in the online classroom this week, this video will supplement our lecture, which we would normally have on Tuesday, November 26th, just right before Thanksgiving break. So instead of having you stay the night before your break to attend lecture, I figured you could watch this video anytime during Thanksgiving week to get all the information you need for the chapters that we're covering right now on the Milky Way galaxy and our own galaxy. So happy Thanksgiving, and let's look at what we need to do this week to cover the material that we're currently studying. Okay, so to start off this week, we do have a lab. So your astronomy laboratory is number 13 this week. You're submitting laboratory number 12, which is your night sky observations and your remote observatory telescope image that you took last week in class with me. That lab and then the forwarded email are both due this Tuesday. So please make sure you submit those via Blackboard. And then go ahead and get started on lab for this week. Now what I encourage you to do is finish watching the rest of this video before you start lab, because it will really help in terms of making sense of this lab this week. But this lab number 13 is classifying galaxies. So galaxies, like you see in this image here, are all different types of galaxies. So far we've started our study of galaxies with our own galaxy, the Milky Way galaxy. But in this lab, you're going to be analyzing the properties of different galaxies in the universe. So different types, being spiral or regular or elliptical galaxies. And you'll get a chance to really analyze what makes these galaxies different and what makes them similar. So with this lab, go ahead and download the lab manual from Blackboard just like you would normally do. Or of course in this image it says from the Collaborate files, but of course we're not actually in the online classroom together, so just go ahead and download the lab manual from Blackboard. It is available to you now. And after you have the lab manual up and ready, go ahead to the Online Galaxy Images resource page. Just go ahead and click on this URL. This will take us to the website where the galaxy images are available to you. So this website just has a long list of galaxies. Okay, so for the first part of your lab, you're going to be identifying various types of galaxies. I give you the galaxy name, for example, M101. You can click on the image to get a bigger view of the galaxy, and you're going to want to do this to really analyze the structural shape of the galaxy. Okay, so from this galaxy, this looks like a spiral galaxy, but then I want you to get more specific. Okay, is a spiral galaxy type 1, type 2? Be as specific as possible. There's also a section for your reasoning. Okay, why did you think it was a type S1 galaxy, for example? Okay, maybe you said because it has tight spiral arms and a small bulge, or spaced out spiral arms and a large bulge, or maybe it's an elliptical looking galaxy because it's fuzzy and round. Okay, give your reasoning for why you think it's that type of galaxy. Okay, so all the galaxies needed for the lab are available on this website, so you can just scroll through and again click on the images. Now when you get to the color images page, that's on the lower part of the website here. So just scroll down and you can see the colored images, and these just get gorgeous. Okay, so these colored images are just beautiful. So take a look at these colored images for the second part of your lab to complete the lab. Okay? So that's lab for this week. So this is due next Tuesday, a week from this week, at 7:30 p.m. before our next week. So complete the lab, ask me any questions via email or phone this week, and work with other students if you're able to. Okay, maybe share this with your roommate. See, it's kind of a fun galaxy looking, or kind of a fun lab looking at these different galaxies. So please share with others and have fun doing this lab. Okay, so that's your lab for this week during Thanksgiving week. Identifying galaxies and filling out the lab manual using this website. Okay, so for lecture this week, we just began our study of galaxies, studying the Milky Way galaxy. We're also going to be studying other types of galaxies. So this is both chapters 23 and 24. And then probably our last week of class after Thanksgiving, we'll cover a little bit extra material in terms of cosmology, which is the study of the universe as a whole. So our Milky Way galaxy, okay, these are visible light images of the Milky Way galaxy from Earth, this bright band of gas and dust and stars visible in our night sky. So when we look into the Milky Way galaxy, we are looking into the plane of our galaxy because we exist in our own galaxy, so we're in the plane. So So when we're looking at our galaxy like this fuzzy region that you're looking at is actually into the plane of the galaxy, and looking outwards, okay, to these other star regions on either side of this band, that's looking out of the plane of our galaxy. So what are just the basic properties of our Milky Way galaxy? Okay, so first off, to begin, our sun lies within the disk of our galaxy. It's about 8,000 parsecs, or that's about 26,000 light years from the center of our galaxy. And the sun actually orbits the galaxy around the center of the galaxy at a speed of around 800,000 kilometers per hour. Okay, that might seem really fast, but it takes our sun about 200 million years to complete one orbit around our Milky Way galaxy. Now, the distribution of gas in the Milky Way galaxy is not uniform. Okay, it's kind of in like a frothy, clumpy mixture. That's how the gas is distributed throughout our Milky Way. And then the sun lies near the edge of kind of an irregularly shaped region where the interstellar medium, just that gas and dust, is very thin and at very high temperatures. Okay, so what do we have in our Milky Way? We have the center region, the disk region, and then this halo region. Okay, so the halo region consists of a spherical region around our flat kind of pancake-like galaxy. And in this halo region exist globular clusters. Okay, these are a class of star clusters associated with the galaxy, but they actually lie just outside the galactic plane, and they have a spherical shape. Okay, they contain up to 1 million stars in a volume less than about 100 parsecs across, or a few hundred light years. So these are very compact, highly dense clusters of stars that are gravitationally attracted to one another. These are the globular clusters. They're very old, they're very metal-poor population 2 stars. And they exist in that outer halo of our own galaxy. Okay, so because these are older stars, it means that they're highly evolved post-main sequence stars. And a lot of times within globular cluster we see some pulsating stars. So that's kind of in our outer halo of our own galaxy. Then we have the disk of the galaxy. That's where our sun lies. Okay, the disk of the galaxy, of our Milky Way galaxy, consists of young, metal-rich population 1 stars, so a lot of main sequence stars. So in the disk is where a lot of star formation is happening. So these are going to have more of our young, hot blue stars on the main sequence and such. Then we have the very center of our galaxy, which is the central bulge. Okay, this is actually a bulge-like, ball-like region. Okay, it contains a mixture of both population 1 and population 2 stars, meaning they're both old and new. And in general, it's kind of a yellowy red color. Okay, it contains a lot of red giant stars or red supergiant stars, so giving it kind of that red-yellow glow. And there's really no star formation going on in the central bulge of our galaxy. So we can look at other galaxies that we think are very similar to ours, and we can kind of see these same features. So here's galaxy M83. So in M83 you can see the central bulge, okay, the kind of yellowy region. Then you have the disk of the galaxy being this blue spiral arm structure, okay, just like our Milky Way galaxy. This is where all the star formation is happening. And you can see that the gas is kind of clumped up in these spiral arm regions, very similar to our own galaxy. Okay, now it's important to remember that within our galaxy, the galaxy itself is moving just like it was. Imagine an old record from like the 50s, right, where you would put the record on and play music. Well, it's one disk. Okay, so as opposed to our solar system where we have the individual planets that orbit around our sun and they're not tied to one another, all the material in the Milky Way galaxy, you can imagine it as one large disk. Okay, so the gravitational attraction is equal around the disk itself. So it causes the stars and the gas and the dust to all orbit in the same direction and all orbit with the same orbital speeds. So they're orbiting together. So essentially we're not following Kepler's laws of planetary motion because it's all one big disk. Okay, so our Milky Way galaxy. Okay, so looking at this kind of pictorial image, the center is the visible matter of the Milky Way galaxy going out to about 50 kiloparsecs. But looking at rotation curves of our galaxy, we find that the speed of the galactic rotation is actually different than what it should be, accounting for all the visible matter we can see in the galaxy. So there seems to be a large amount of matter or mass that is unaccounted for. Okay? And so what we have found is that the total mass of the galaxy, including all the stars and all the matter that we can see, doesn't equal to the total mass that we're assuming is there due to how the galaxy is rotating. So what we think is that there's what we call dark matter. Okay? And it makes up like 90% of the rest of the mass that we kind of see as missing in our galaxy. Okay? And this dark matter is, in a sense, just a presence by the influence of the orbits of the stars and the clouds within our galaxy. So the dark matter of our galaxy is thought to be in a spherical halo centered on the galactic nucleus, so something like this in this image here. A spherical halo that could be up to about 100 kiloparsecs or more in diameter around our own galaxy. So an analysis of the rotation curve of our galaxy indicates that the density of the halo decreases as you get further from the center of the galaxy. So perhaps the density of this dark matter actually decreases as you get further from the galaxy. So this dark matter is really an assumed matter because essentially we measure more mass than we can actually visually account for in our galaxy. We say due to rotation curves and gravitational attraction there should be this much mass. When we add up all the mass of the visible matter we can see, visible matter being the stars and the gas and the dust, there's not enough mass there. So there's this dark matter, this kind of extra mass that astronomers can't see, and that's what we call dark matter. So what is dark matter? Okay, there's a few proposals for what scientists think dark matter is, but we don't know what it is quite yet. Okay, so a couple of proposals. First proposal is that this dark matter halo around our galaxy is composed of, at least in part, of some kind of dimensional object with masses less than 1 solar masses. Okay, these could include something like brown dwarfs, white dwarfs, black holes, any kind of compact halo object. And we call these machos. Okay, so some kind of massive, what we call a massive compact halo objects, which is what a macho is. So these could be things like brown dwarf stars that we're just not seeing, maybe different white dwarfs or black holes that are accounting for this extra mass. So astronomers have detected machos, but they don't really account for all the dark matter that we think should exist in our galaxy. So that's one proposal, but it doesn't seem to quite be enough. Okay, another proposal is that maybe the remainder of the dark matter is something much more exotic, something like, let's say, neutrinos with a very small amount of mass. So maybe there's a lot of them with a significant amount of mass could actually contribute to a bulk of the dark matter in the galaxy. That's one thought. Okay, we're not quite sure. Or maybe there's a new class of subatomic particles, okay, called weakly interacting massive particles, or WIMPs. Okay, their existence is suggested by theories, but they're not really confirmed yet experimentally. Okay, other galaxies have similar rotation curves as our galaxy does, indicating that maybe these dark matter halos do exist. Okay, so maybe there are some new types of particles like these WIMPs out there, accounting for this extra matter. So it's still a mystery, but we have this extra mass that we're not quite sure why it exists. Okay, but we just think there's something out there and we're calling that something dark matter. Now, at the center of our galaxy, and what scientists are finding, and you've actually heard this a bit in some of our weekly news presentations this year, is that most galaxies tend to have a black hole at the center. Okay, we're finding that this is kind of being true, that at the very center of the galaxy there seems to be a lot of emission of infrared and X-ray and radio wavelengths, indicating there's a very strong radio source located at the center of our galaxy. And this radio source is what we call Sagittarius A star. So you read that as Sagittarius A star. And all it really is it's a radio source at the center of our galaxy, emitting in the infrared and the X-ray. And what scientists have finally concluded is that this region is actually a supermassive black hole at the center of our galaxy. with a mass of about 4 times 10 to the 6 solar masses. Okay, so this region exerts a very large force on the material around it. In fact, it's about 45 astronomical units in radius. So, how do we know there's this black hole at the center of our galaxy? Well, first of all, let's look at some infrared images, looking at the infrared and X-ray and radio sources coming from the center of our galaxy. So this is looking at the center of our galaxy on the left here of an infrared view, and then zooming in to the galactic center. Okay, so the reason it's called Sagittarius A star is from Earth. It's in the region of the constellation Sagittarius. Okay, so as you zoom in, it's somewhere right in here. Okay, it's very, very close to the center of the Milky Way galaxy. There's hundreds of stars within just 1 light year of this region. And what we're able to do is we're able to monitor the motions of the stars in the immediate vicinity of Sagittarius A star with essentially infrared detectors. And what we see is that the stars are orbiting this central region with speeds in excess of 1,500 kilometers per second. And what we see is that they're orbiting around something that isn't quite there visually, but it is there in the infrared, in the X-ray, and the radio, and that is how we see black holes. Okay, this gravitational sink. Okay, very high mass with almost no volume. Okay, infinite density. So here's another image. Okay, here's the radio source coming from the center of our galaxy, and then the X-ray images coming from the center of our galaxy, all indicators of the supermassive black hole at the center of our galaxy, which isn't really that unique. We're finding black holes at the center of lots of galaxies. Okay, so one cool way that we can actually see star motions around the center of the black hole, and one way that astronomers are able to detect that this black hole exists, is by tracking how stars close to this region actually move. So this plot is actually going to be showing how stars move around this central portion of our galaxy, and you're going to see that this gravitational curve is actually causing stars to orbit around it. And this is the plot that you're going to use in your homework for chapter 23, that last question. Let's go ahead and take a look at this. So you can go ahead and click on the URL, and it'll take a moment to load up here for a second. Okay, so these are all stars within the vicinity of Sagittarius A star, and the application will run on its own, and these are paths of the star's motion around the black hole. Now it's actual data, and then as it gets higher into the years here, they actually use supplemental data. So it's actual data year after year showing where the stars are in position. So let's go ahead and watch it again. Here's the stars moving. This one completes a full orbit, this little blue one here, okay, to show the exact location of this black hole. Okay, so these are stars at the center of our galaxy, and astronomers are plotting the motion of these stars, and the reason they're moving around this center is due to the black hole. So it's important to remember that a black hole is just a very massive object, so stars aren't always going to be sucked in or falling into a black hole. Only matter that gets within what's called the Schwarzschild radius will actually fall in. Everything else is just going to orbit around this high mass object, because essentially it's acting like a high mass star. Okay, so that kind of concludes our Milky Way. So our Milky Way galaxy, how would you describe it? There's a question on your homework that I want you just to describe the Milky Way galaxy in your own words. So a kid comes up to you and says, hey, what is the Milky Way galaxy? What would you tell them? Okay, maybe something like, it's a compact region of gas and dust and stars in a flat pancake-like plane that's all orbiting in one disk region. You could explain to them how it has spiral arms and kind of a lumpy texture, how star formation is taking place in our galaxy. Perhaps the fact that there's a black hole at the center of our galaxy, and explain to them what a black hole is. Okay? On that homework question, I want you to explain as if you were explaining to a friend. Describe to them what you know about our Milky Way galaxy. Okay, so let's move on to chapter 24 in your textbook on other galaxies. So, our Milky Way galaxy is just one of billions of galaxies in the universe. So the first observations of galaxies were called nebula, okay, because they could see some structure, okay, but they just thought they were nebula. Okay, they thought they were these dusty regions. They couldn't quite see them with high-power telescopes that we have now, so they called them spiral nebulas or nebula regions. Okay, so M51, which we now know is a spiral galaxy, they called it a spiral nebula. Okay, but as we were able to really start analyzing the structure, we realized that these weren't nebula, they were actually galaxies. So I love this image. This is an image, the first image of Hubble Deep Field. And essentially what Hubble did back when it first took these images in 1996 was it essentially pointed Hubble at a dark area of space. Something where there was no stars, nothing. Just a blank dark area. And they took a picture. And here's what came up in the blank dark area of space. Definitely not nothing. Okay, billions of stars in this picture here. Okay, so galaxies everywhere. So different types of galaxies in this image. So literally this was an image taken by Hubble where they just pointed out to a dark region of space, and sure enough it ain't dark out there. Okay, we have so many galaxies, billions of galaxies out there. In this image alone you can see elliptical galaxies, spiral galaxies, irregular galaxies. Okay, just billions of galaxies out there. It's amazing. Okay, so let's think for a second. So you're able to look at different types of galaxies in the night sky. How would you classify galaxies? So I want you to take a moment and think about this, just like we would do if we were in class. So here's some images of different types of galaxies. Okay, how would you classify them? Would you classify them by color? Okay, I see reds and yellows and blues. Perhaps by size. Small galaxies, large galaxies. Maybe by shape. Okay, there's some spiral structure, elliptical structure, globular structure, circular structure, spherical structure. Or maybe would you use some kind of other classification scheme? So take a moment. How would you classify galaxies if you were the one starting to classify galaxies? Okay, so depending on what you said, the first man to really start classifying galaxies was Edwin Hubble. Okay, now Hubble, he decided to classify galaxies based on size and shape. Now it doesn't mean if you thought color would be a good indicator, that is a good indicator. Okay, but just to start off, Hubble was kind of the first astronomer to really start classifying galaxies, and he decided to classify these galaxies by their size and their shape. So this is Edwin Hubble, okay? And of course he's named after the largest telescope that we have that was taking these first initial images of galaxies. Okay, and so what Hubble did was he used Cepheid variable stars to measure the distance to what he thought were these nebulas, okay, or these galaxies. And so what he did was he's able to discover that the universe is made up of billions of galaxies. And he was one of the first scientists to really start studying kind of the universe as a whole. And so when we talk about studying the universe as a whole, we call this cosmology. Okay, not cosmetology, but cosmology. So it's the study of the universe as a whole, how it formed, how it has evolved, how it is today, and then actually thinking about theories of how the universe will end. So that's cosmology. And Hubble, in terms of his study of galaxies, was really one of the first cosmologists. Okay, and Hubble, he classified galaxies essentially into four broad categories, okay, based on appearance. Okay, meaning what do the galaxies look like? Okay, and what he noticed that galaxies are made up of a large number of stars, but they come in a variety of different shapes and sizes. And so that's how he decided to start classifying galaxies. And we call this the Hubble classification scheme. And it really is still used today, even though we know there's kind of sub-classifications off these schemes, but it's the main classification schemes. So we classified galaxies in terms of spiral, elliptical, barred spiral, and irregular. Okay, so for example, M51, which is the spiral galaxy located near the Big Dipper, Okay, he described this as a spiral galaxy based on the fact that it has spiral-looking gas and dust arms. Okay, Andromeda Galaxy, M31. Okay, another type of galaxy. You can really see a shape difference here. Okay, so his Hubble classification scheme is based off of 4 broad categories. Now, there really is kind of a 5th category that I'll talk about a little bit later. But the Hubble classification, all based on appearance, classifies galaxies into spirals, designated by a capital S, barred spirals, designated by SB, ellipticals with an E, and irregular galaxies, indicated by IRR. So let's look at these. Okay, so spiral, elliptical, irregular. Now, nowadays, we also consider irregular or dwarf galaxies. And this last one I want to kind of talk to you about is active galaxies. Now, this is kind of a new subset of galaxies we've introduced. Active galaxies are galaxies essentially that have some kind of very large black hole activity happening in the center. Okay, sometimes these are also indicated as quasars. So kind of a more modern take on this are the same ones that he had: spirals, barred spirals, ellipticals, irregulars. We'll add dwarf galaxies in with irregulars, and these active galaxies as well. Okay, so let's go through the basic of Hubble classification. So spiral galaxies. Okay, what are these? So spiral galaxies have arced lanes of stars and gas and dust, just like the Milky Way. So the spiral arms are made up of young, hot, blue stars, those population 1s. There's a lot of H2 regions, therefore there's a lot of star formation happening. So spiral arm galaxies, a lot of star formation happening in the spiral arms. Now spiral galaxies, most of them have a pretty distinct central bulge, okay, that yellow-red color indicating older stars with maybe lower metal content and very little star formation. Now, Hubble classified further to be more specific than just spirals. He classified 3 different types of spirals: SA, SB, and SC. I think I have a slide on this. Yeah, okay. So spiral type A, so the capital S is for spiral, lowercase a for type A. These types of spiral galaxies are more smooth, and they have broad spiral arms, okay? And they have a very fat central bulge. Okay, so let's look at this on the lower left image. This is a type A. So you can see that the central bulge is huge and that the spiral arms aren't very distinct. Okay, that would be an SA. So when you're working on the lab, you're going to be identifying galaxies. So this is how you want to start thinking about how to identify different types of galaxies. Alright, let's look at the SB galaxy here in the center. So spiral type B galaxies, well, they have moderately well-defined spiral arms and a moderately sized central bulge. Okay, so M31, the Andromeda Galaxy, and M51, the spiral galaxy in the Big Dipper, near the Big Dipper, are essentially spiral type B galaxies. So they're kind of like the middle spiral galaxies. You can start to see more distinct spiral arms and a moderately sized central bulge. Now let's look at spiral galaxies type C. Okay, look at this tiny bulge and very distinct spiral arms. Okay, so spiral type C, designated by capital SC. Those spiral arms are narrow and well defined and have a tiny central bulge. Oh, sorry. Let's look at these one more time. So A on the left, B in the middle, and spiral type C on the right. So those are your spiral galaxies. Okay, what about barred spirals? Well, these are spiral galaxies, but the spiral arm structure is originating at the end of a bar-shaped region in the center of the galaxy. So our Milky Way galaxy might be a barred spiral galaxy. Okay, we think that maybe our central bulge is a little bit peanut-shaped. Okay, but it's definitely a spiral galaxy overall. So again, Hubble has designated subclasses under barred spirals. So we have barred spiral type A on the left, B in the middle, and C on the right. So take a look at these differences. Again, central bulge is bigger with less defined arms. Okay, in type C's, very defined spiral arms, and you can really see the bar shape of this central bulge on the type C. Okay, so let's look at these again. So barred spiral, SB, type A, large central bulge, tiny, thin, wound spiral arms. Type B, moderately sized bulge, moderately wound spiral arms. And type C, okay, lumpy or loosely wound spiral arms, okay, really separating off the galaxy here. And a tiny central bulge that's more elongated. Okay, those are the three types of barred spiral galaxies. Alright, our third type of galaxy are the elliptical galaxies. Okay, these elliptical galaxies have no spiral arms. Okay, they're the rounder, fuzzier, red-looking galaxies. And we classify these actually through numbers. So we go through E0 through E7. So capital E is the designation for elliptical. So E0 galaxies are the roundest, and E7 galaxies are the flattest. Now, these aren't really the true shapes of these galaxies, it's just how it appears to us from Earth, okay, how it looks to us from Earth. So as you can see on the images here, on the left image, E0 galaxy is a lot rounder, and then this E6 galaxy is a lot more elliptical, okay, flattened out. So these galaxies are mainly made up of old red population 2 stars with small amounts of metals, okay? And from radio and infrared observations, we see that these galaxies are devoid of interstellar gas and dust, and that star formation has ended a long time ago in these galaxies. So that essentially just leaves the older red stars without those new star formations happening. So that's why they look more red in color. Okay, there's not a lot of new stars being formed. They're all the kind of redder, older, dying stars. So, giant elliptical galaxies are very rare. Okay, and giant elliptical galaxies are like 20 times larger than the average galaxy. But dwarf elliptical galaxies we are finding are very common. Okay, there's only a few million stars in dwarf elliptical galaxies compared to the 100 billion stars in the Milky Way. Okay, but there seems to be a lot of them. In fact, these dwarf elliptical galaxies sometimes are so thin that you can actually see straight through them. Oops, I think I did that slide twice. Okay. So here's some examples of giant elliptical galaxies on the left, and then these dwarf elliptical galaxies are these just tiny little things in here. Okay, so dwarf elliptical galaxies on the right, giant elliptical galaxies on the left. Okay, so between the ellipticals and the spirals, sometimes we have what we call lenticular galaxies. So this is a plot, essentially, or chart of the Hubble classification of galaxies. It's called the Hubble's tuning fork diagram. Okay, so you can see the elliptical galaxies, and then it branches off into the spirals and the barred spirals. Now, in between the ellipticals and the two types of spirals, sometimes we have what we call lenticular galaxies. These are kind of lens-shaped galaxies that have a central bulge and a disk, but really no spiral arms. Okay, maybe you could think of lenticular galaxies as armless spiral galaxies. Okay, they're kind of somewhere in between. Okay, so, sorry, I just wanted to check that slide real quick. So Hubble's tuning fork diagram. So really, this diagram is supposed to be a summation of the classification of galaxies. So Hubble thought when he made this that it would represent an evolutionary sequence of galaxies. But really, that's not what astronomers think this plot is indicating anymore. The more modern interpretation of the diagram is that it's just an arrangement of the galaxies according to overall rotation. So that the elliptical galaxies on the left side of the image of the plot have little internal rotation and therefore no disk shape. The spiral and the barred spiral type A galaxies, they have enough overall rotation to form a disk, but the central bulge is still very big. And And then as we move to the spiral type Cs, the both barred spiral and regular spiral type Cs, these galaxies have the largest rotation. So the central bulge is smaller, and most of the gas and dust is in the disk instead of in the central bulge. So that's kind of how you could interpret this diagram now, is more about overall rotation of the galaxies. Higher rotation for the spirals, low rotation for the ellipticals. Now, the galaxies that don't fit these classifications are these irregular galaxies indicated here on the far right of the image. So irregular galaxies. These are the galaxies that don't fit into the scheme of spirals, barred spirals, or ellipticals. In general, irregular galaxies tend to be rich in interstellar gas and dust, and they have both young and old types of stars. So Hubble defined two types of irregular galaxies. Okay, he defined irregular type 1 and irregular type 2. Now, about 10% of known galaxies are actually irregular galaxies. And if you've ever been lucky enough to go to the southern hemisphere, you might have been able to see what we call the large and small Magellanic Clouds. Well, these are not really clouds, but instead they are irregular type galaxies. And this image in the background here is a large and small Magellanic Cloud. So those are actually irregular galaxies that you can see from the southern hemisphere. So irregular type 1 and irregular type 2, the two designations of irregular galaxies that Hubble made. So irregular type 1 galaxies, they only hint, there's only a little bit of hints towards some kind of organized structure. Okay, they have a lot of O and B type stars, some H2 regions, and the large Magellanic Cloud and the small Magellanic Cloud are really classified as irregular type 1 clouds. Okay, and these are actually galaxies that are near our own Milky Way galaxy. Now the irregular type 2 galaxies, they tend to be asymmetrical and really distorted in shape. And they seem to have been caused maybe by the collision, some kind of collision with other galaxies, or some kind of violent activity within their own nucleus of the galaxy. So very irregular shape in these guys. The irregular ones have some hint towards some kind of organized structure. Okay, so here's the large Magellanic Cloud up close. Okay, as you can see, it's just kind of got some kind of structure to it, a little bit elliptical, but not much spiral shape, maybe a weird kind of bulge, just very irregular in general. Okay, so just a little bit review here for you. Concept question: which galaxy type has the oldest stellar population? So which galaxy type has the oldest stellar population? So think about old stars. What color are old stars? That might help you. Is it the spirals, the barred spirals, the ellipticals, or the irregulars? So which galaxy type has the oldest stellar population? So take a minute and think about that. Okay, so what did you decide? Which galaxy type has the oldest stellar population? Alright, those elliptical galaxies have the oldest stellar population. They're reddish in color. There's no new star formation going on. So no blue stars, no young hot stars. They're all old red dead stars, those elliptical galaxies. So they contain the oldest stellar populations. So hopefully you got that right. Okay, what about these active galaxies I mentioned? Okay, kind of the next range, these active galaxies. Well, these active galaxies, sometimes they're so active that they look like stars, but they're stars that emit large amounts of energy as radio waves. Okay? And when they're so bright at the center that they look like stars from our location, we call them quasars. So quasars are really an active central region of an active galaxy. Now these quasars, or these active galaxies, have extremely large redshifts, okay, which means that they are very, very, very far away. In fact, quasars are some of the farthest away objects that we have discovered yet. Okay, and there are these active central regions of these galaxies are believed to originate from a black hole at the center of a galaxy. So since they are so far away, when we detect these objects, these quasars, it's essentially like looking back in time, because we're seeing light that has taken that long to get to us. So quasars are really the oldest objects we have observed in the universe. So essentially they are objects that we're looking at that were formed when the universe was very young, and their starlight is just now getting to us here on Earth. So it's really exciting to study quasars because we're essentially looking at the young universe. So here's an image of a quasar. Okay, it's a very bright star-like looking object, but it's actually the central region of a very active galaxy, emitting a lot of energy in the infrared and radio and X-ray. So these quasars, emitting these large amounts of energy, radio and X-ray, okay, they release an extreme amount of radiation, and they're extremely luminous, and that luminosity is more than just thermonuclear reactions, right? It's not really starlight, it's energy coming from the central galaxy itself. So in visible light, you see the star, and it happens to be these jets of radio and X-ray particles spewing out from either side of these active galaxies. And you actually see these in a close-up image. So these are very active galaxies. Okay, so here's a good question for you. Do you think galaxies exist independently, or do you think they're parts of groups of galaxies? So do you think galaxies are independent, or do you think galaxies exist in groups? What do you guys think? What do you think? Okay, so galaxies actually exist in groups. They are not necessarily individually out there. So galaxies are not necessarily scattered randomly throughout the universe. There tends to be what we call either poor clusters or rich clusters. So poor clusters are just meaning smaller amounts of galaxies clumped together. Now we are part of a local cluster, okay, which is a poor cluster, and we call that cluster our local group. So us, the Andromeda Galaxy, the Virgo cluster, those are part of our local group. Now, richer clusters are more compact, highly dense galaxy clusters. There's lots of galaxies in them. And the Virgo cluster, which is near us, is a rich cluster of galaxies. So let's take a look. Here's our local group, okay? Our local group of galaxies. So you can see the Andromeda Galaxy is a big one, M31 in there, and then our Milky Way kind of being at the center there. Okay, so beyond just like local galaxies, local groups of galaxies and these rich galaxies, there's also, we also can further group our galaxies into what we call superclusters. So we have our own local group, and then our nearby Virgo cluster, that rich cluster. Together, those galaxies and a few other galaxy groups, we lump together into what we call a supercluster. Okay, and these superclusters are not necessarily bound by gravity, okay, but the local clusters and the rich clusters are gravitationally bound to one another. So what does that mean? Well, within our own local group, our galaxy and the Andromeda Galaxy are actually gravitationally bound to one another. So that means that the Andromeda Galaxy is actually moving towards us, okay, because it's gravitationally bound to us. But then galaxies in a supercluster, they're not necessarily bound by gravity. Okay, and we'll talk about the Hubble law in just a little bit. So our local supercluster consists of our local group and the Virgo cluster and a few other galaxy groups, like this image is showing. Okay, so because galaxies exist in these groups, it's not too uncommon for galaxies to collide. So two galaxies from a group or from a nearby cluster of galaxies absolutely can collide. Okay, and we see it happening throughout the universe. So two galaxies are gravitationally attracted, they can interact. In fact, the Andromeda Galaxy and our Milky Way galaxy will most likely interact and collide over time. So what can result from this collision is that interstellar gas and dust can be stripped from the galaxies. This can cause new star formation to start in these colliding galaxies, okay, meaning that protostars can actually form. And this is where we get a merging of galaxies. So two galaxies moving together can actually start more star formation and combine to form either one kind of weird galaxy or a large galaxy again. Okay, so here's some animations. Here's some animations of mergers of galaxies. You can check out this YouTube video on your own here. So here's just it's a computer simulation of what the merger of galaxies would look like over time. Okay, so two galaxies near each other, and then over millions of years as they get closer and start spinning and interacting. You can imagine all this dust and gas interacting and mushing together would definitely start star formation. Hot regions starting stars. So take a look at this video when you get a chance. Okay, I'm going to stop here, and we're going to cover just a little bit about cosmology after we get back from our Thanksgiving break. So far, go ahead and read chapters 23 and chapters 24 in your textbook, and that's the material that will be covered in your homework and also in the lab that you're doing this week on identifying different types of galaxies. So your homework and your lab, your lab is due next Tuesday, your homework is due at the end of the semester, and we will finish up on cosmology on Tuesday after Thanksgiving. So have a great Thanksgiving. I will post all this online, and I will see you guys for our last week of classes on the first week of December. All right, have a great Thanksgiving, everyone.